So hi everyone, I'm Nicolas and I'm working in the Latmos and I will present you what I've done with the nitride oxide NAGLO simulated by the Venus planetary climate model. So first, let's discuss about the origin of this NAGLO. So as presented by Frank Mills this morning, it's pretty much the same process of creations. On the day side, you have the photolysis of dinitrogen and carbon dioxide that produce nitrogen and oxygen atoms that are brings to the night side through the solar to antisolar circulation. And in the night side, they're going down in the atmosphere where the density is increasing. And so they can combine with each other and produce photons. The photons are both in UV wavelengths, so they can be seen by instruments. So this altitude of this NAGLO is about 115 kilometers. And so why are we interested in this NAGLO? It's for two reasons. First is because it's a tracer of the dynamics at an altitude where the solar to antisolar circulation and the zonal superrotation are mixing together. So it's really interesting. And it's also a tracer of the nitrogen chemistry, one of the few observable that we are in our possession. So let's talk about the data that we have for the NAGLO. So in the left, you have observation from OUVS from Pioneer Venus. And in the right, you have observation from SPICA from Venus Express. So we express the NAGLO NADI observations in Rayleigh because they are integrated observations. And so the main features that you can see in these maps is that the emission bulge is shifted towards the morning side, which is a result of the interaction of the two circulations. So for this work, I'm working with the Venus PCM. So it has already been presented by Sébastien and other people this morning. Just to remind you, the model resolution is about 1.8 degrees of latitude and 3.8 degrees of longitude. And we have a 90 level of pressure, so the model goes up to 250 kilometers. So the first step was to implement the nitrogen chemistry. So it means 8 new species. 4 of them are neutral ones, and we have also their young counterpart. We have 3 new photolysis linked to the nitrogen as a new species added in the model. And we have also 13 new chemical reactions. The most important one for this project was the combination with nitrogen and oxygen, and also 16 new ionic reactions. So when we added the nitrogen chemistry, we had to ensure that the nitrogen profiles were correct with the observations. We used Pioneer Venus observations, and the main source of nitrogen is coming from the photolysis of dinitrogen, and the photolysis of dinitrogen is not very well known. There's a factor of a few on this photolysis. And so to have this good agreement between the observation and the model, we had to multiply the photolysis rate by a factor 2. So now we have everything to modelize our NAGLO emissions. And so in the left, you have SPICA data. What's in black is where we don't have any informations. And on the right, you have output of the model. And so the first thing you can see is that in the model, the bulge of the NAGLO is shifted towards morning side as in the observation, which is good. But you can also see that the intensity of the emissions is lower in the model than in the observations, where we have about 9 kilo Rayleigh in the maximum, and in the model about 4 or 5. So the second result is this little animation where this is the evolution of the nitric oxide NAGLO every terrestrial day. So what you can see there is a strong short time scale variability in the model that is also seen in the observations. When we were focusing on the vertical distributions, you can see that we have the strong short time scale variability in the position of the nightglow, but also in the intensity. We goes from 1,500 to 2,500 photon per centimeter cube per second. And the most important thing you can see there is there a strong correlation between the position of the bulge of the nightglow and the wind on the altitude where the maximum is. So if we take a look at average profile of the distribution of the nightglow, in red is the data from Stephen et al. 2012, which is Picard limb observations that are inverted and average. And in green, this is the mean result from the model, a bit average between 20 and 30 degrees north and between midnight and 4 a.m. And in blue is the 1 sigma distribution. And what you can see there is that we are succeeding to produce the same peak emission for the model. You can see also the strong variability in the intensity. And we have a shift about 5 kilometers in the altitude of the emission. So if the peak of the emission is the same in the model and the observation, you can ask why the integrated value is not the same. It's because our peak is much more narrow than the observation. So when you integrate it, of course, our value will be lower than the observations. So to conclude on this modelization of the nitric oxide nightglow, we are succeeding in reproducing the shift toward the morning side. We are succeeding in reproducing the strong short time scale variability, and the peak intensity when we average match with the SPICAV observations. But we have still points to improve. For example, the integrated intensity, which is underestimated by factor 2, and also the altitude of the peak, which is about 5 kilometers higher in the models and the observation. So if we can give some hint about what we can improve, we can think about the solar to anti-solar circulation. We have something also a bit strange when we see about 100 kilometers, we have like super rotational winds that should not appear, and we don't really know why for now. And so in the future, what we should have to do is to work on the causes that cause the differences between the observation and the model. And also we can work on the oxygen nightglow, which is really interesting because it's only about 20 kilometers apart and have a completely different shape. And so we can use both of the emissions at the same time to have a better constraint on the dynamics on the model. So thanks everyone, and I will be happy to answer your question later.